Hi everyone, thank you for joining my presentation today. My name is Esmaeil Mottaghi and I'm going to present my thesis titled Integrating Generative Design and Surrogate Modeling for Data-Informed Exploration in the Early Phases of Building Design. My presentation starts with an introduction explaining the research problem, goals, and background. Then I will discuss the research process and system design, followed by conclusion and future works. Early design decisions in architectural design is important because it can influence environmental impacts and project costs more than later phases. Designers employ various design exploration and performance assessment methods to meet design requirements and produce well-performing designs to reduce environmental impacts and enhance sustainable built environment. Designers use generative design approach using algorithms and computer-aided processes to generate large design datasets. Designers also use machine learning surrogate models to replace simulations which are computationally expensive and time-intensive processes. Through an iterative process of specify, generate, and evaluate, designers generate design forms and performance. Design forms refers to geometry-related data such as building height and window-to-wall ratio, and performance refers to energy consumption, daylighting, thermal comfort, and so on and so forth. However, the generative design and performance prediction produces a large volume of diverse design data, spatial and non-spatial, numerical and geometrical, which is cognitively overwhelming. Although generative design and performance prediction are highly related tasks, they are disjoint activities in the current practice, since they rely on different workflows and tools. So, new workflows and tools are needed to integrate design generation and performance prediction. Our proposed solution to address this problem is adopting design analytics to integrate design exploration with data analytics to guide data-informed design decision-making using interactive data visualizations. We define two main objectives. First, to develop design analytic interfaces that supports decision-making by integrating generative design and performance prediction. To achieve this, we ask how can design analytics interfaces integrate generative design and performance prediction. Second, what design workflow can apply this integration. Third, what are the high-level requirements for design analytics interfaces? The second objective was to evaluate the acceptance of a design analytic interface in real-world practice. Based on that, we asked questions to evaluate usability, utility, and adaptability of the interface. Let's continue with the background research. I will go over the key concepts that form the foundation of my work, focusing on three main areas: generative design integrated with building performance simulations, machine learning based surrogate modeling, and design analytics interfaces. First, let's discuss the integration of generative design with building performance simulation. Generative design employs algorithms to quickly generate multiple design alternatives, optimizing performance criteria such as daylighting and energy use. This approach, as highlighted by Caldas, significantly enhances the efficiency of design processes. Moreover, integrating parametric tools with building performance simulations allows for earlier stage exploration, bridging creativity with performance as emphasized by Anton et al. Furthermore, studies by Bernard et al. Demonstrate how the integration of generative design and building performance simulation can effectively balance energy efficiency with daylight optimization, which enhances sustainability of architectural design. Next, we explore how machine learning-based surrogate modeling can substitute traditional simulation methods. Surrogate modeling is particularly effective in reducing computational time and labor, enabling faster performance prediction in earlier stages of design. as shown by Westerman and later studies by Youssef and Blujon as well as Zorn et al. For example, Youssef et al. Used surrogate daylighting models to explore complex floor layouts, while Zorn et al. Demonstrated the use of these models in real-time dashboards, allowing for continuous performance updates and more informed design decisions. Finally, let's look at design analytics interfaces, which play a crucial role in integrating design exploration with performance data. As Erhan discussed, such interfaces allow for a more informed and efficient decision-making process using interactive data visualizations. Examples of tools that use design analytic interfaces include DANS, DStar, DesignSense, and NetZero Navigator. These tools employ various data visualization techniques such as parallel coordinates and graphical representations to compare and evaluate design alternatives effectively. Studies by researchers highlighted the importance of these visualizations in enhancing the design decision-making processes. In this study, we followed the design study methodology for problem characterization and analyzing a real-world problem faced by domain experts and design a visualization system that supports solving their problem. We also integrated agile and use case driven software development methodology to iteratively and incrementally develop the prototype. This integration involved collaboration with domain experts through weekly sprints, allowing for continuous refinements and developments of requirements and prototype throughout the research process. Based on a literature review, we collected the high-level requirements. The first set derived from creativity support tools principles, supporting exploration, storing and retrieving alternatives, as well as keeping a history of alternatives and actions, and supporting different design styles. And the second set comes from reviewing a literature review and expert review, providing simple and engaging interactions with design model and surrogate models to be usable for varying expertise levels, providing sensitivity analysis as well as interactive data visualization for those who are familiar with. Considering the high-level requirements, we proposed a workflow integrating generative design and performance assessment with design analytics interfaces. In generative design process, designers define the parametric model to generate design alternatives and compile design data. The performance assessment adds a layer of information to the design data by selecting, predicting, and organizing the performance data using machine learning driven surrogate models. Now, design analytics merge, analyze, and visualize the design data using interactive data visualizations, and this step guides for generating more design datasets through generative design processes. We propose two design analytics interfaces in this research. The first DPredict version was a low-fidelity prototype building on high-level requirements and proposed integration workflow. DPredict involves two main tabs: data generation and comparison. The data generation tab supports design generation, performance prediction, utilizing machine learning-based surrogate models for various performance metrics. Design data visualization and repository for collecting plausible design solutions. The interface supports different design generation methods. Single iterative design generation using sliders to adjust parameters and generate design alternatives iteratively. Multiple alternative generation by assigning discrete or continuous values to each parameter for sampling the design space. History tracking was also supported to monitor and retrieve previous actions on demand, either by selecting previous alternatives on PCP or sliders. Sensitivity analysis was an interesting feature of DPredict version 1. where designers can get insights into each building parameter influence on performance metric, either by ranking the parameter according to their influence of a performance metric, or visualizing performance metric trends through a line graph for individual parameters. And comparison view is where generated and collected data can be compared, analyzed, and guide designers for data-informed decision making. Building on the low-fidelity prototype through an incremental development, we developed a functional prototype called Dipritic version 2 over 11 months and through 140 versions in weekly sessions by collaborating with expert architects from our industry partner. This prototype contains three main parts: parametric controllers, performance analysis, repository, and comparison. This prototype is connected to a machine learning-based target model developed by Perkins and Will research team to predict daylighting metrics, and it's also connected to EPC, which is an open source Excel-based energy calculator to calculate heating and cooling need using local weather data. DPredict version 2 supports 7 main use case scenarios. First is model setup. Designers can use Rhino objects to define the building outline, interior walls, and context buildings. And following that, the openings and shading devices can be generated and adjusted parametrically. Openings can be generated or removed one by one, group by group, or all at once as you see. Once the model is ready, the surrogate model and EPC starts to generate and predict daylight and energy data. And interface shows the results with some data visualizations such as heat maps and stack bar charts either on the model or on the interface. As the parametric model changes, the performance prediction continuously responds to the changes and displays the results with data visualizations. Now, the design alternatives can be saved and collected in the repository as designers explore the design space. So, alternatives are always ready to be retrieved on demand. Designers can investigate and compare the collected alternatives side by side using their numerical performance data and 3D or 3D images. Or designers can select an alternative and retrieve it for further inspection. To evaluate the utility, usability, and adaptability of the interface during the development process, we conducted a formative expert review to collect feedback and comments to refine the requirements and prototype. We recruited 7 expert architects with more than 5 years of experience from our industry partner. This process contains 4 main steps. First, a study description, consent form, and questionnaire. Second, presenting system features and workflow, which took around 15 minutes. Third, asking participants to perform main use cases, which took around 1 hour. And finally, conducting a semi-structured interview to collect detailed feedback on the system features, ease of use, and adaptability. The last 2 steps were screen recorded. I summarized and categorized their feedback into 3 groups: usability, utility, and adaptability. Regarding the usability, we received positive comments. All participants appreciated the ease of use and speed of the prototype, and 5 out of 7 participants mentioned that the interface was easy to learn. In terms of utility, participants praised the features such as comparative analysis, visual feedback on building performance, and how they could see, compare, and learn from the interface to modify their designs and make better decisions. Finally, they could see themselves using this performance-based design exploration interface in their current workflow and mentioned they will recommend it to their colleagues. To sum up, we aim to develop design analytics interfaces by integrating generative design and performance prediction to enable data-informed decision-making in early phases of design exploration. We propose two design analytics interfaces to solve the domain problem using interactive data visualizations, the Predict version 1 and 2. In conclusion, performance-driven interactive platforms can partially support early stage informed decision-making. Utilizing the proposed framework in the Predict improve the design exploration efficiency. The data-driven approach maintains the exploratory and nonlinear nature of the design process. Despite the achievements, we face some limitations. We only used one machine learning-based surrogate model. In the future, we will involve more surrogate models for various performance metrics. Modeling environment was another limitation since we only used Rhino environment. And using available user interface in Rhino didn't allow us to apply interactive visualizations in version 2. Moreover, alternatives incrementally built as one set. We should improve the interaction with alternatives to use multiple sets. And finally, number of participants in our expert review was limited to 7 participants. We will engage more participants in the future expert reviews. In future, we will improve interactivity of design analytic interfaces using general purpose APIs. We implemented multiple alternative generation using discrete or continuous sampling in the next version of DeepPredict. Sensitivity analysis, which relies on multiple alternative generation, is also partially implemented in version 3. Recently, we have tested the interface on real-world projects and we plan to report the results in future publications. This is a screenshot of the Predict version 3, which is under development by SFU and Perkins and Will research team. Thanks for your attention.